Let's continue on functions and their graphs. We're going to move on to last section on chapter 1. It's on section 1.9. We're going to talk about the inverse functions. Okay, so learning objectives, we'll learn how to find the inverse functions formally, informally, and formally verify the two functions are inverse functions of each other. Secondly, we use a graph of functions to determine whether the two functions have inverse functions. And also, we learn how to use the horizontal line test to determine whether functions are one-to-one or whether functions have an inverse function. Okay. And last one, find the inverse function algebraically. And that's four major, outcomes we try to accomplish here. And first of all, inverse function, we typically write this. Inverse is f inverse of f of x. And this notation indicates this is the inverse function of f of x. So now that we know that sets of order pairs represent a function. For example, let's say we have a function f of x equal to x plus 4, and we can generate some order pairs yx equal to 1, y equal to 5, so 1, 5 is one order pair, and yx equal to 2, y equal to 6, right? So setting 2 to 4, you get 6. X equal to 3, 3 plus 4 gives us 7. X equal to 4, 4 plus 4 gives us 8. And if you're interchanging the first and second coordinate, meaning x coordinate and y coordinate, you basically form the inverse function of f of x. So for inverse function, x becomes y, and y value becomes x value. We use this inverse notation to represent it. So secondly, if you look at inverse function here, x minus 4, when x equal to 5, 5 minus 4 gives us 1, so 5, 1. When x equal to 6, 6 minus 4 gives us 2. 7 minus 4 gives us 3. 8 minus 4 gives us 4. If you look at it, exactly the switching the x and y values from the previous order pairs. And so the main thing about the inverse function is original function and inverse function, they undo each other. So that's very important characteristics of those two functions. So they undo each other. And then the domain of the original function becomes range of the inverse function. Okay. And then a range of the original function becomes a domain of the inverse function. Domain of f becomes a range of inverse function. And then range of the original function becomes a domain of the inverse function. Range of original function becomes the domain of inverse function. Okay, then if you compose original function with the inverse function, then you do the composition of original function composed with the inverse function, or the inverse function composed with the original function, we end up with the identity function. So that explains why they undo each other. For example, like f inverse, f composed with inverse function, we get f of x minus 4 because inverse function becomes x minus 4. And if you plug it in, we end up with the identity function x. If you do inverse function composed with the original function, f inverse of f of x becomes x plus 4, then again we end up with the identity function here. Okay. And if you want to find the inverse of f of x equal to 4x, and we also want to verify that f composed with the inverse, and then inverse composed with the original function f of x equal to identity function. So the function f, you see, multiplied each input by 4. And to do this, you need to divide each input by 4. So we come up with the inverse function of this becomes. So algebraically speaking, you just first of all write this, and then you change f of x to y. You get y equal to 4x. Now interchange y becomes x, and x becomes y. Now you solve for y, and so y equal to x over 4. Now again, you turn the y as the inverse notation f inverse of x. Yeah, so that's how we end up with this inverse function if you do it algebraically, but intuitively, you see, since they undo each other, so we know that it must be x over 4 to be the inverse function. Okay, so you get the inverse function. Now we just have to verify that f of x equal 4x, inverse function equal x over 4. So now, first of all, let's see what is verified first one, f composed with inverse function. So f inverse function is x over 4. Now we go back to the original function, replace x with the given expression x over 4. And we should end up with the result. I'll go back to the original function now. It's 4 times x over 4, that turned out to be x. So we verify that it's identity function. Secondly, let's verify inverse composed with the original function. So the inverse original function is 4x. Now if you look at it, we should have in the inverse function replace x with 4x. So we get 4x over 4. Again, we end up with the identity function x. So they undo each other. Eventually, when you find a composition of those two, it always becomes x. So that f and g, two functions such that f composed with g is x, and then g composed f is x. Okay, area x in domain G and area x in domain F. Under these conditions, function G is the inverse function of F, and G is denoted by F inverse, right? F with -1, power on top right hand corner. We usually pronounce the F inverse. It's not the same as reciprocal. This is not representing a reciprocal, it means F inverse. So F composed with the inverse function becomes x. Inverse function composed with the F function, it's also equal to x. So the domain of function f of x must be equal to range of the inverse function. The range of the original function f of x must be equal to the domain of the inverse function. So domain becomes range, range becomes domain. Okay. And those are important, aspects of the inverse functions. So this -1 here doesn't represent in the reciprocal, right? It represents inverse. So function g is the inverse function of function f, and then inverse function of mutual relationships. It's a mutual relationships. If f is inverse of g, then g must be the inverse of f. That's what we call the mutual relationship. And for this reason, we know that f and g are inverse function of each other. Now, if you look at the graph of the inverse functions, it will be symmetrical with respect to the identity function. So look at this. If this is original function f of x, then the inverse function is f inverse of x. Then they form a mirror image based on identity function y equal to x. So every point a comma b lies on the graph of f. Then b comma a must be located on the graph of inverse function, vice versa. So that means x becomes y, y becomes x, which is exactly the identity function. Identity function serves the purpose of x equal to y, y equal to x. Okay. And if we sketch the graph of inverse function f of x equal to 2x minus 3, and then inverse f inverse equal to half x plus 3, they will form a mirror image. They are refraction of each other with respect to the line y equal to x. And this is how you look at it. And so this is f of x. And if you look at all these order pairs right here, -5, -1, you can find a -1, -5, right? Corresponding like order pairs in another, here, this one becomes that. Just switch x and y, you get a coordinate for the inverse function. And they form a mirror image based on identity function y equal to x. And if you look at these order pairs right here, for the inverse function, you just switch x and y, you get an order pair for the inverse function. So x becomes y, y becomes x. You can do the same thing so in order to generate the order pair for the inverse function, you have order pair for the original function, and then just switch x and y, and you get an order pair for the inverse function. All right, that's how you just sketch the graph with the inverse properties. And inverse function must be one-to-one functions. So we utilize this test called horizontal line test to test for the inverse functions, existence of inverse functions. So horizontal line test for the existence of the inverse function. So function f has inverse function if and only if no horizontal line intercept the graph of function f of x at more than one point, meaning horizontal line can only have one intercept, no more than one intercept. Okay, so if no horizontal line intercept the graph of f of x at more than one point, so no y values match with more than one x values, that guarantees one-to-one. So one y value corresponds with one x value. One y value corresponds with one x value. And that's a requirement to have an inverse function. So this is essential characteristics of what we call a one-to-one function. So a function f is one-to-one when each value of dependent variable, meaning y values, corresponds to exactly one value of independent variable x value. Then the function f has inverse function if and only if f is one-to-one. Okay, so for example, let's say we have original function f of x equal x squared. Now we come up with the order pairs, picking -2, -1, 0, 1, 2, 3, and get all the y values by just plugging the x value into the function and get all these order pairs. Now, if you switch x and y, right, this is y right here. then get this order pair. Now you will notice that although f of x equal x squared is a function, but right here, this x value, same x value produces two y values. So the inverse function, so here, one x value produces two y values. So it's not a function, so it's not one-to-one. That means f of x equal x squared has no inverse function. So that means f of x equal x squared has no inverse function. By just simply switching x and y, you can easily make a determination about that. And if you draw the graph, as you can see, y equal x squared, right? This is f of x equal to x squared. If you draw any horizontal line, you're gonna have two intercepts all over the place, right? So that means for any given y value here, you're gonna create two x values. So it's not one-to-one, so therefore it has no inverse function. Okay, so horizontal line tests help you a lot in terms of determining the existence of the inverse function. We look at this function f of x equal to x cubed minus 1. Now this one has inverse function because anytime when you draw the horizontal line, you only have one intercept. You can draw as many as you like. Always have one intercept that indicates for each y value here that exists one and only one x value to be paired with the given y value. So because there's no horizontal line intercept the graph of f at more than one point, so f is one-to-one function, and it does have an inverse function. Okay. Not like this one, x squared minus 1. And time you draw the horizontal line, you're going to have two intercepts, which tells us for any given y value here, you end up with the two x values. So it's not one-to-one. So therefore, it has no inverse function. And the last learning objective here is about finding the inverse functions algebraically. So we're going to follow the certain procedure, right? So first of all, you have a graph of the function, then you can use a horizontal line test to decide whether function f of x has inverse function. Okay, so if you have the graph, if let's say you do not have the graph, then you could jump right to the equation for f of x. First of all, replace step 1, replace f of x with y. Okay, step number 2, interswitch x and y, or interchange the roles of x and y. So y becomes x, x becomes y. And after that, solve for y. Interchange x and y. Then solve for y. And after that, write the y with the inverse notation. Replace y with the f inverse of x. And that's it. And ideally, you probably want to verify that f composed with inverse function because identity function, also inverse function composed with original function, it becomes identity function. So once you have done all those 5 steps, you actually not only find the inverse function, but also verify the inverse function. So last step is verifying. Verify they are inverse functions of each other. Now let's follow the procedure and let's find the inverse function of this rational function. F of x equal to 5 minus x over 3x plus 2. So step number 1, f of x becomes y. So you get y equal to 5 minus x over 3x plus 2. Okay, and step number 2, y becomes x, and then x becomes y. Right? We do that as step number 2. Step number 3, we're going to solve for y here. So make it proportion, solving for y. So 5 minus x goes to the left. I guess I'll do it on the next slide. And I'm just first of all show you the graph first, and then we're going to do it in the next slide. And so first of all, if you look at this graph, we get this graph of the function, and if we draw the horizontal line here, you only have one intercept. That indicates this function does have an inverse function. And then we could, since we have the graph, we utilize that, apply the horizontal line test to determine the existence of the inverse function. The next step, and let's go through the procedure to find the inverse function. And step number 1, then f of x becomes y. So step number 1. Okay, so now we get a 5 minus x on the left over 3x plus 2 at the bottom. Now step number 2, y becomes x. Now x becomes y, so 5 minus y over 3y plus 2. Again, make it proportion, cross multiplying, and we get a 5 minus y. Okay, you know what, let me just, I think write the other one is more convenient. So I'll do x times 3y plus 2. So step number 3, we're gonna solve for y. Then 5 minus y times 1 goes to the right. Now we distribute it, and we get a 3xy plus 2x equal to 5 minus y. Now in order to solve for y, we need to add y from both sides of the equation and subtract 2x from both sides of the equation. I guess I'll do this. Subtract 2x from both sides of the equation. Okay, so y get cancelled on the right, 2x get cancelled on the left. So you get 3xy adding y, that's equal to negative 2x adding 5. Now factor out y. 3x plus 1 equal negative 2x plus 5. Okay, now we just divide both sides of the equation by this x terms, 3x plus 1. And cancel that y's by itself. And eventually we end up with negative 2x plus 5 over 3x adding 1. And then eventually we just replace fourth step, replace the y with the inverse notation, and we got it. Negative 2x adding 5 over 3x adding 1. Okay. We'll come up with the original function and inverse function, and let's copy that. Let's verify this f of x equal to 5 minus x over 3x plus 2. And just find the inverse function, and we'll make sure, we find the right thing. Minus 2x plus 5 over 3x plus 1. Okay. Well, step 1, we're gonna check this. F composed with inverse function. So this is f inverse function, we replace with this. Okay. So it's f of negative 2x plus 5 over 3x plus 1. Now again, we go back to the original function and replace x with the given